Hello everyone. For this particular lesson, I thought it would be best to show you how to do this through a video because then you can follow along with these questions from your blank copy. This completed copy, as you can see, is already available, and so you've got something to look at when you go through and do the practice. So what I'm going to be showing you how to do today is using the mole ratios, which is what your lesson 5 was, and now combining it with some masses to determine what's called a yield of product. So first of all, this process of using masses and moles to determine yield has a special name in chemistry. It's called stoichiometry. It's silly sounding, but stoichiometry. And it means the measure of the mass of elements or compounds found in a reaction. So how this is going to work is you're going to be given the mass of the limiting reagent always. And then you're going to convert that mass into moles. Use the moles and the mole ratio to get to your moles of product. And then once you have your moles of product, convert it back into mass so that you have what's called a yield. So a yield is the amount of product that you obtain in a chemical reaction, and it's measured in mass. There are two types of yield, the theoretical yield and the empirical yield. The theoretical yield is the one we get using the stoichiometry calculation. So it's using our periodic table, punching in some numbers, and calculating an answer. It would be the answer we would get if we were to carry this out experimentally and we had an absolutely perfect experiment, no errors. This is the mass that we should be getting. The empirical yield is what we actually get when we carry out this reaction experimentally. Because experiments have errors, mistakes can be made, the reactants don't always behave as they should. Sometimes what we actually get in the lab doesn't match what we're supposed to get according to our math. So what we can do with that, if they're not the same, and rarely will they be the same, we can carry out a calculation called the percentage yield. And what this is it tells you how efficient the reaction is. So to give you an example, let's say you had a test out of 50. So that means theoretically you could get a perfect test of 50 out of 50. But then you do the test and you have some errors and you only get 40. So now your empirical yield would be 40 marks. You should have got 50 marks, so we can determine now what your test percentage is. So to get your test percent, we take what you got on your test and we divide it by the total. Well, that's exactly what this is about. So if we were supposed to get 50 grams of a product and you only got 40 grams in the experiment, what is your percent yield? So what you do is you take your empirical yield, so that would be your 40 marks, divide it by what you should have got, which is the total, 50 marks, multiply by 100, and you get 80%. So for you as a test, that's probably pretty good. But when it comes to a chemical reaction, that is not good enough. To have a good, efficient experiment, your percent yield should not be any lower than 90 and should not be any higher than 110. So this is deemed the percentage for an effective experiment. So I'm going to show you how to do all of this. It's repetitive. You'll be doing the same thing over and over and over, which is nice because you'll learn how to do this quite well. So steps we're going to be carrying out to do our stoichiometry is the first thing we're going to do is we're going to write a balanced equation. So a balanced chemical reaction. That's the very first thing that you have to do, okay? And then the first thing you're going to do after that is you're going to convert your mass of your limiting reagent into moles of limiting reagent using the equation that you learned about last week, N is equal to little m over big M, your molar mass equation, okay? Once you've done that, now you're going to convert those moles, your moles of limiting reagent, into moles of product, so whatever product you want, using the mole ratio. And the mole ratio is what you learned about in lesson 5. So I'm going to show you how to do that today when we do the practice in case you weren't sure. Then the third thing you're going to do is you're going to take those moles of product that you just calculated and you're going to convert it into mass of product, of product using M equals NM. So what you've got is you have a mass calculation here, mass to moles, using this equation. Then you're going to use your mole ratio to go from your limiting reagent to your product. That will give you your moles of product. And then you want to convert those moles of product into mass, because masses we can work with. We understand grams. We can measure grams on a balance or a scale, but we can't measure moles. So that's why stoichiometry is the process of starting with masses of your limiting reagent and ending with the mass of product on the other side. And this mass of product is your theoretical yield. So that's what we refer to as our TY, short form. Okay, so that is what we're going to do. And then once we have our mass of product calculated, then we'll get our, the question will give you your empirical yield, and then you can determine the percent, okay? So let me go through and let's do this example together. So in a lab process, a student carries out a chemical reaction where she reacts 35.8 grams of magnesium with silver bromide. So the first thing you have to do is write out the balanced chemical reaction. So we're going to have magnesium, which is a solid, plus silver bromide, which is AgBr, and it's aqueous. Remember your rules. And then this is a single displacement reaction, so magnesium will kick out the silver, and it will come out alone on the other side. And then magnesium is going to pick up the Br. Magnesium is a +2 charge, and when you go to your solubility table on your periodic table, you will see that magnesium bromide comes out aqueous. And then last thing we do is balance 2, so we need a 2 in front, and then because of this 2, we need a 2 in front. So remember your moles. So you have 1 mole of magnesium reacting with 2 moles of silver bromide to produce 2 moles of silver and 1 mole of MgBr. So remember, if there's no number in front, it's just assumed to be a 1. So that's the first thing we're going to do. And then it tells you here that it's giving you this mass of magnesium. So that means that's what we're reacting. So this is going to be our limiting reagent, which means this is going to be our excess reagent. Okay, so we're going to use this, and we want to determine the theoretical yield of metal. So we want this here. So we're going to start with this, and we're going to go across our reaction over to this. So remember your steps. The first thing you're going to do is you're going to convert your mass of Mg into moles of Mg, and then go from there. So we're given this 35.8 grams. This is what we're given. And what we want to find on the other side is this. We want to go from here to here. So the first thing we're going to do is you're going to find your moles of Mg, which is your Lr, because you can only use the Lr to get yields of product. So remember your equation, M equals moles times molar mass. We're going to rearrange for N. So you're going to divide out the M on both sides. So when you divide out the big M, it cancels on the right side. What you do to one side of the equation, you do to the other. So rearrange, it'll be little m over big M. Okay, so this is not rearranged, solving for mass. This is rearranged, solving for moles. Little m over big M. Okay, so N is little m over big M. Little m is 35.8 grams. And we're going to divide that by the molar mass of magnesium. When you go to your periodic table, it's 24.305 grams per mole. And you're going to plug that in your calculator, 5.8, 0.305, and you'll get 1.47295 moles of Mg. Now this is not a final answer. We're not done. We have to go from mass of magnesium to mass of silver. So we've done the first step. We've got moles. So why do we need moles? Because to use a mole ratio to go from one substance to another, you need to have moles. So now what we're going to do is our mole ratio. And the mole ratio is going to be mg to ag in your equation. Okay, so the fraction we're going to make is our moles of mg from the equation, which is 1, and use our moles of ag in the equation, which is 2. So we need to take our moles of magnesium, so our 1.47295 moles of mg. Now, what's the fraction that we want? Well, remember your rule from lesson 5. It's always your moles of product in the equation that goes in the numerator. So 2 moles of Ag, and we're going to divide that by 1 mole of Mg. Now, why is the product on the top and the limiting reagent always on the bottom? Because what happens is now is that these moles of Mg will cancel these moles of Mg down in the denominator, leaving you with moles of silver. So all we've done is we've built a bridge. We start at Mg and we're building our bridge to get over to Ag. We're converting magnesium moles into silver moles. And the only way to do that is to take your moles of magnesium that you calculated and multiply it by the ratio of the coefficients in the reaction. It's always the product over the limiting reagent. Always, always 100% of the time. So your product moles over your limiting reagent moles. Some people say what you want to find over what you're given. We want to find silver, we're given Mg. So 2 moles over 1 mole. So you're going to take this number that's still in your calculator and you're going to multiply it by 2 and divide by 1. And when you do, you're going to get 2.9459 moles of Ag. So we've just converted moles of magnesium into moles of silver. So this is still not a final answer because we don't care about the moles of silver. We can't measure out 2.9 moles of silver. So what we're going to do now is we're going to find our mass of silver. And this is going to be our theoretical yield. That's what we want right there. So remember your formula. Mass is moles times molar mass. So the moles we have right here of silver, 2.9459 moles of Ag. And we're going to multiply that by the molar mass of silver. And the molar mass of silver is 107.868 grams per mole. And so when we multiply these moles, you can just leave the number in your calculator, by 107.868, we get 317.768 grams. So now we got to go back. This is our final answer for A. This is our theoretical yield, but we need it to be in proper sig figs. So when you go to the question, 35.8 is 3 sig figs. So we want 3 sig figs. So we can say, therefore, our theoretical yield of silver, if we're cutting it off after 3 sig figs, which would be here, this 7 rounds this 7 up to an 8, it'll be 318 grams. And that is our theoretical yield of silver. So what does this mean? Well, it means that if I gave you exactly 35.8 grams of magnesium, and you completely reacted it, used it all up, and had some excess silver bromide left over, on the other side of the equation, you should produce exactly 318 grams of silver. Exactly that mass. That's the theoretical yield. Okay, so now we're going to go to part B. So this was A. Part B. So let's say if you produced from your experiment only 305 grams, so that's your EY. So your EY is 305 grams. Okay. The question is asking you to determine the percentage yield. So percent yield is your EY over your TY times 100. So you're going to take your 305 grams divided by 318 grams, multiply by 100, so 305, and you get, and when you take that multiply by 100, you need 3 sig figs, so 95.9%. So that's your theoretical yield. So the last question I asked, is this effective? Is this a good experiment? Well, remember your rule. To have a good reaction efficiency, your percent needs to be between 90 and 110. So you're allowed 10% error below 100 and 10% error above 100. And this is definitely above the 90%. So we can say, yes, this is effective. The percent yield is greater than 90%. Okay, it's between 90% and 110%. So this means if you actually collected 305 grams of silver in your experiment, you're 95.9% close to getting to what you should have got. So that would be deemed a really good experiment. Okay, so same steps every single time. Balanced equation. Take your mass of LR, convert it to moles of LR. Use those moles of LR and then your mole ratio, your fraction from your coefficients with your product to get the moles of product that it converts to, and then convert those moles of product back into mass. So you have a mass step, a mole ratio step, and then another mass step. Okay, and then you'll have a question about percent yield. You'll be given either given your empirical yield, or you'll be given the percent and asked to solve for the empirical yield. Okay, so let's do another one. Okay, so the second one, you want to determine the theoretical yield of product when 0.0350 grams of aluminum reacts with excess oxygen from the air. If the reaction efficiency is 75%, so this time they're going to give you the efficiency, and this is not a good efficiency because it's below 90, how much product was actually made. Okay, so the first thing we're going to do is write a balanced chemical reaction between aluminum and oxygen. This is a synthesis, so ALO, aluminum has a +3 charge, and the oxide ion is a 2, and it's a solid. So when we go to balance, start with the compound, we have 3 O's and 2 O's. So the lowest number they both multiply into is 6. So we have to turn this into 6, this into 6. Now you have 4 ALs, and that goes over here. Okay, so it's giving you the mass of aluminum with excess O2. So this is your LR, this is your ER, and the mass that you're given is 0.0350 grams, and what we want to do is find the mass of this. So if you set up your equation, this is where we're starting, this is where we're going, so we have to build a bridge to go from aluminum to aluminum oxide. That bridge is the mole ratio. Well, to use a mole ratio, you need moles. Grams is not moles. So the first thing we're going to do is you're going to find your mass of AL. Or sorry, not your mass, your moles. Sorry about that. So let's change that here. Okay, so you're going to find your moles of AL. That's the first thing you're going to do. So N is little m over big M. Little m is always given. It's the 0.0350 grams. And your molar mass of aluminum from your periodic table is 26.982 grams per mole. So now we can do that division, 0.0350, 26.982, divide that, and we get 0.001297 moles of AL. So what that means is 0.035 grams of aluminum is equivalent to 0.00129 moles of aluminum. So now we have our moles of aluminum, we can do our mole ratio with our product to get our moles of product. So that's what we're going to do next. So we're going to do our mole ratio, and our mole ratio will be of AL to Al2O3. Those are the two. This is your limiting reagent, this is your product, and you're going to take the coefficients from the balanced equation. So we're going to take these moles of Al, 0.001297 moles of Al, and we're going to multiply it by the product coefficient over the limiting reagent coefficient. So the product coefficient is 2 moles of Al2O3. The limiting reagent coefficient is 4 moles of Al. And what you'll notice is these moles of Al cancel out these moles of Al in the denominator, allowing us to convert moles of Al into moles of Al2O3. So you're going to take this number here, you're going to multiply it by 2, and then you're going to divide it by 4, and you're going to get 0.0006485. So sometimes these numbers are going to be really big, sometimes they're going to be really small, like this one here. Okay, and that's our moles of Al2O3. So now the last thing we need to do is we want the yield. The yield is mass. You always have to take your mass. So we're going to find our mass of Al2O3. So mass is moles times molar mass. Well, we know the moles. What we don't know is the molar mass. So what I do is off to the side over here, I calculate my molar mass of Al2O3. So all of you know how to do this because you did it way back when in one of your previous lessons. So Al2O3 is 2, and when you're calculating your molar mass, it's always the compound. Ignore this number in front because this number is a mole, molar mass is a mass. So just write out the formula for the compound as it's written and calculate it. So you have 2 aluminums at 26.982, and you're going to add to that 3 oxygens at 15.999. Plug that into your calculator, and that will give you your molar mass of aluminum oxide, and you'll get 101.961 grams per mole. So now we can go over here and take 0.0006485 moles, and we're going to multiply that by 101.961 grams per mole. And when we do that, we get 0.0661 grams. Going back to the question, sig figs, these first front 2 zeros do not count because they don't follow a number. The 3 and the 5 count, and this 0 counts because it follows a number, follows the 5, and there's a decimal point. So you have 3 sig figs. So we have exactly 3 sig figs here. So our answer is good the way it is. So we can leave it like that. Okay, so that's our answer there. And now what we want to do is go to part B. So remember, this is our theoretical yield. So in theory, if we were to react 0.035 grams of aluminum, we should produce exactly 0.0661 grams of aluminum oxide. So now it says we have a 75% efficiency. What did we actually make? So think of it this way. If you got 75% on your test, and your test was out of 0.0661, how would you get your mark? So if you think of your test, if you were to look at your test, it's X over, let's say your test is out of 50. Let's do an example here. Okay, you got X out of 50 and you got 75%. What is X? How do you solve for X? Well, you would cross multiply. Okay, and convert your percent into a decimal. So that's what we're going to do, but instead of with a test mark, we're going to use a percent yield. So we know that percent yield is EY over TY times 100. Okay, and that times 100 just means that we're going to take this, multiply it by 100, because this is always going to be a decimal. So if you want to know so if I get rid of this now, let's leave this out for right now, and you want to solve for EY. This is your X here, and this is your total which is this number here. So you're going to have 75% equals EY over 0.0661 grams. What you need to do is convert this into a decimal. So divide by 100. So 0.75 is equal to EY over 0.0661 grams. To solve for EY, you're going to multiply this out on both sides. So therefore EY, so all you're going to do to get EY is take your percent yield as a decimal and multiply it by your theoretical yield. And you do that 100% of the time, and it will always work. Okay, so we're going to take our 0.75 and multiply it by 0.0661, and you'll get 0.0496 grams. So that's your empirical yield. So if you take your 0.0496 grams and you divide it by 0.0661 grams, you will get 75%. Okay, so in terms of your formulas, remember percent Y is EY over TY times 100. And if you want your EY, all you're going to do is take your percent Y, divide it by 100, so you get a decimal, and then you're going to multiply it by your TY. That's how you would solve for it. I was just rearranging an equation, a percent equation. Okay? All right, so let's do another one. So number 3, what we have here is we want the mass, what mass of the theoretical yield of precipitate is made when you have 14 grams of potassium chloride reacting with excess sodium oxide. So this is going to be a precipitation reaction, and what we're looking for is the precipitate in our reaction. So we're going to take potassium chloride, so KCl, and we're going to react it with sodium oxide. We're going to do a double displacement reaction. So potassium is going to pick up the O. So potassium is a +1 charge. Oxide is a 2. This is solid according to your solubility table. And then the Na will pick up the Cl, which is aqueous. And you have 2 Nas here. So we need to put a 2 in front. That gives us 2 Cls. So we need a 2 over here, and we have 2 Ks here. So this is your balance equation. So it's telling you here that sodium oxide is the ER. This is our LR because we're given a mass of 14 grams. So this is where we're starting, and the precipitate is this here. So we want the mass of this. So we don't care about the sodium oxide. We don't care about the supernatant, the salt, the sodium chloride on the other side. We want to start with this and go to this. So the first thing you're going to do is find your moles of KCl. And N is always little m over big M. Well, big M we have to calculate. So off to the side here, M of KCl. So you go to your periodic table, and the molar mass of KCl is 39.098. And we're going to add that to 35.453. And when you add those two numbers together, that will give you your molar mass of the compound, which is 64.551 grams per mole. So now we can go over here. We'll take our 14 grams. We'll divide it by 64.551 grams per mole. And that will give us our moles of KCl. So 0.21688 moles of KCl. Well, now that we have the moles of KCl, let's use our mole ratio to get our moles of K2O. So that's the second thing we're going to do, is our mole ratio. And the mole ratio will be for KCl to K2O. LR to product. Okay, and in the fraction, the product always goes on the top, the LR always goes on the bottom, so that we can cancel out those LR moles. So we're going to take our 0.21688 moles of KCl, and our fraction comes from our coefficients. And so this is a 1, so it's 1 mole of K2O divided by 2 moles of KCl. And what you'll notice is these moles of KCl cancel out these moles of KCl in the denominator. We just built our bridge. We've gone from moles of KCl to moles of K2O. So we're going to take this number already in your calculator from up here, multiply it by 1, divide by 2, and you will get 0.10844 moles of K2O. So we've just converted moles of LR into moles of product. We don't want it in mole form because we can't measure that or picture that, so we want to find the mass. So we're going to find our mass of K2O. And mass is moles times molar mass. So we have our moles from up here. What we don't have is the molar mass. So let's go over here and calculate that, the molar mass of K2O. So we're going to take, K is 39.098 from up here. There's 2 of them in the formula, and the molar mass of oxygen is 15.999. So you're going to calculate that, and that will give you your molar mass of K2O, which is 94.195 grams per mole. So now we can go over here, take our moles that's already in your calculator, 10844 moles, multiply that by 95.195 grams per mole, and that will give you your mass, which is your theoretical yield. So 10.2146 grams. Going back to the question, we only want 2 significant figures, so we're going to cut it off there, and so we can say therefore our theoretical yield is 10. Now how do you make 10 into 2 sig figs? Put the decimal point after. Now that 0 counts, and you're done. So your theoretical yield is 10 grams of K2O. So what that means is that if you fully reacted 14 grams of KCl, because these are in a 1:2 ratio, convert the 14 grams to moles, use that 1:2 ratio to get your moles of product, and you should produce exactly 10 grams of this precipitate when the 14 grams of KCl reacts. That's what you should get. So the question says that in your lab you actually got 9.2 grams. So for part B, your EY is 9.2 grams. We want to know our percent Y, so that's our EY over TY times 100. So we're going to take 9.2 grams divided by 10 decimal grams, so 2 sig figs, 2 sig figs. So think of it this way. If you had a test out of 10 marks and you got 9.2 marks out of 10, what is your percent? So you're going to take 9.2, divide it by 10, multiply by 100, and when you do that, you're going to get exactly 92%. So that means you would have got 92% on your test. Is this good? This is efficient. It's a good reaction. And that's because we're between 90% and 110% efficiency, which is what you want. Okay? All right, I'm going to do one more with you. Again,